EC 111 Lecture 10 Set 3 Random Access Memory. On FPGAs, typically we have the memory inside the LUTs, but we also have, because memory is such an important element, in particular for big data analytics, where we have information that needs to be stored or processed with a lot of data, we need a lot of memory on the device. Typically, even the device memory is not enough. We have to go off chip, which we will be discussing at the end of this lecture. But in order to have a little bit more memory in the FPGA, we typically have these random access memory elements, which are called BRAM inside the design. And the BRAM is to transfer data between different clock domains. Typically on one FPGA board, you may have not just one clock, you may have various clocks, and for that we have the phase lock loops that are helping us to change the frequency of the clock system. We may be able to transfer data between FPGA and another processor that is outside, even between FPGA boards, or we can do more data analytics using the block RAMs, because the memory that we have inside the LUTs is rather limited. Now, in the single port configuration, if we have a block of RAM that has a single port configuration, again, we have similar construct like we've seen before. We have write enable, clock enable, and we have the output and both synchronous, asynchronous reset. Of course, the clock address, data in, and data in parity. Again, for data out, we both have the data out and data out parity. And the reason we have these parity bits is that there is a danger of having more errors on the BRAM. So the memories are not perfect; they can have errors, and the parity helps us to detect those errors if we have a few of those errors to fix it. So, the function is pretty simple, as you could imagine. If enable is disabled, then there's no action. If we have the enable signal and we don't have the write enable, then there's no write operation. If it's enabled and the write is enabled, then we have the we are going to write to the currently address place in the memory. We could also have a dual port configuration where we can have one memory array with dual write and read ports. So per clock cycle, we could have 2 writes and 2 reads. And the dual port does not offer priority resolution. So if you have write collision, the memory location becomes undefined. If you want to make sure that you don't have a collision, you have to put additional logic to do that. And that's something that is really on the shoulder of the programmers, because we don't have this conflict resolution for the priority between the ports. So if you write data, the question is what data appears on the data output port, and this is a question that we need to address with a blocking versus non-blocking assignment, because that tells us at which point of time what was written in each location. So, when you do write first, there are 3 different modes. There is the write first mode, where there is the write first mode, read first mode, or no change. In the write first mode, the input data is going to be assigned to the data out, and the memory address is going to, the data in is going to go to that memory address. In the read first, we are going to first get the data in to the memory address, and the data out is also going to read the memory address. And in no change, we just have the data in going to the memory address. So basically, when you're writing, the data that was in there is going to be read out, and then the data in is going to go to the memory address. If you're reading, the same thing is just going to stay there. It's not going to change it. We could either infer RAM in Verilog, or we could instantiate it. Here is a example of an inference of a RAM. Again, we have the same knobs as we were showing in the previous example. We have the clock, write enable signal, address, and input output, and the array which we are writing to. And if we are doing a read first mode, what we are going to do is we are going to if this is write enabled, but we are in the read first mode, we are going to assign to the input we are going to assign the input data to that address, and then the same time we are going to assign to the output the content of this address. And because these are non-blocking assignments, means that when the clock comes, the output is going to read the value of the RAM at that address right at the edge of the clock, and the input is going to be written right to that same place. So these two values are not necessarily equal, because at the edge of clock the values are not set. This is a non-blocking assignment. In the write first mode, we are going to assign the DI also to the DO. So this is basically a different value, because here the DI value is going to be the same for both cases. So this is going to be. So the problem with this code is that, as you've seen here, we have 128 locations, but here the address is only going to point to 6-bit, and this is going to be a problem. So you need to verify your assumption about the memory before making to avoid typical mistakes such as this one. You could also infer other types of RAM with asynchronous data port by doing this blocking assignment, which makes asynchronous read. The reason for this asynchronicity is that here the non-blocking assignment on the to the values makes sure that on the arrival of the edge of the clock, this value is going to be written to this piece of memory. But here we are using an assign statement, which is blocking, which means that we are doing an asynchronous read. This is not synchronized with the clock. This is every time you're updating the value, this is asynchronously is going to read the value into that operation. And, one thing to remember is the block RAM is a synchronous module. Address is only captured on the clock edge. So if you want to use the BRAM module, you need to infer this synchronicity or use this synchronicity in the code. Here is another example of a dual port RAM. Similarly, we could have one write port, two read ports, and you could also have synchronous read. And the synchronous read here is because the addresses here are clocked. So these change at the clock edge. And once this changes, then we assign this output port for output port A and output B to these two addresses. So even though this is a blocking assignment, because the addresses are only changing at the edge of the clock, we are in effect making a synchronous read in this case. So the previous examples were showing how a RAM could be inferred, but of course block RAMs are important modules. So we have libraries that instantiate that. The primitive block RAM in Spartan 3 are of this form, which is something that selects the configuration. In Intel boards, there is a different primitive for selection, such as this. So you could use the initialized RAM as BRAM as a lookup table or as a read-only memory, and the initial contents of the BRAM are just specified by the bit stream. And you could use initial block, which is a synchronous command that runs only in the beginning of the code, and then that could set the values in the BRAM. Or you could use readmemb or readmemh system calls that you could load values into the BRAM. And this ensures that the values of your RAM are initialized to what you want in your configuration. So this is another RAM in Verilog, which is inferred, and this is initialized. The way this is initialized is using initial command, and as you see here, initial command is pretty portable, so you could use it on any different board. We are not using any library, but every time you have an initial statement, it only runs in the beginning of the code, and it's a clocked statement. It's a synchronous statement. It's going to initialize the values of this RAM. In this particular example, it's just going to initialize this to number 0 to 63 for the 64-bit addresses that we have. In readmemh, what this is going to do is, it's going to read a file which is supposed to be somewhere in the synthesis tool. So accessible to the synthesis tool. So in this particular case, it's hex data. We're going to use the command $readmemh to read this data into the RAM, and then put the size and the address for this hex data that goes into this. Next, we will be learning about memory arrays.